In this video, I want to derive the volume of an n-dimensional sphere. And from the volume, you can also derive the surface. But we will be actually concerned with the volume of an n-dimensional sphere. We will start from the following integral in n dimensions. So we will integrate over Rn, let me write it properly, e to the minus x squared. And then here I have the differential that will denote dnx. dnx is simply dx1, dx2, dxn. And how do we interpret x squared? Well, x squared is shorthand. X squared is defined as x1 squared plus x2 squared plus x3 squared and so on, all the way up to xn squared. Now, due to the properties of the exponential, we can also rewrite this integral as a product of integrals of the following form: e to the minus x1 squared, then we have dx1, and then we take the power n of such an integral. So if we raise it to the power n, basically what we are going to get is we are going to get an n-dimensional integral, and when you take the product of all the exponentials by changing the name of the variable, you're going to get this e to the minus x squared. But now, since we are integrating over Rn, of course here we are integrating from minus infinity to plus infinity. So in this case we are integrating over R. If you want, you can also write it like this. And by means of multivariable calculus, this integral can be evaluated. There is a trick to do so. I'm not going to do it here, but this integral is just the square root of pi. So the result here of this integration is pi to the power n over 2. However, there is also another way of computing such an integral. In particular, let me rewrite it. We have integral over Rn e to the minus, if you want, we have x1 squared plus x2 squared plus xn squared dnx. Now, this integral can also be written in another form, in particular if we use spherical coordinates. In spherical coordinates, in 3 dimensions, so we have x1 squared plus x2 squared plus x3 squared. If we go to spherical coordinates, we know that this is equal to some r squared, which is a radius of a sphere. You can think that r is just the radius of the sphere. And when you go to spherical coordinates, dx1, dx2, dx3 is equal to r squared. Then you have the sine of a certain angle, theta, and then you have dr, d theta, d phi. Now you can put together r squared dr, and then you have sine theta, d phi, which is just the solid angle d omega that we have in 3 dimensions. Something similar can also be done in n dimensions. In particular, this will be equal to r squared, but in this case, of course, we have n variables, so this will be an n-dimensional sphere. So the n-dimensional sphere will satisfy the equation x1 squared plus x2 squared plus xn squared equal to r squared. And then this differential, this product here of differentials, will become equal to r to the power n minus 1 instead of 2. So here we are in 3 dimensions. So if n is equal to 3, 3 minus 1 is equal to 2. Then we have the differential of the solid angle, which will be different from this expression here. It will be more complicated. We don't need that expression. So I'm just writing down d omega here. And then we have dr, like this. So the integral can be written in the following form. We integrate e to the minus r squared, r to the power n minus 1, dr d omega, like this. Omega will not depend on r, therefore this integral here will factor. And it will factor like this. We have an integral over r from 0 to infinity, because r is a positive quantity. e to the minus r squared, and then I'm going to rewrite r to the n minus 1 times dr in the following way. R squared to the power n over 2 minus 1, and then here I have the differential of r squared, and then I divide by 2. So it is quite easy to see that this is coincident with this, because dr squared over 2 is just equal to r dr multiplied by 2 divided by 2. So it's just r dr. This is just r dr. When this r multiplies that term, so we have r squared to the power n over 2 minus 1, which would be r to the power 2 times n over 2 minus 2, and then we get a plus 1 from this. So you can see that we get r to the power n minus 1, which is exactly this. So it is quite easy to realize that indeed we have simply rewritten in another fashion the same integral. And then we are left with the integral over d omega. And we can define this integral here to be omega sub n. So this is the solid angle that we have in n dimensions. We can call it omega sub n. It's not so important how you label it. You just have to understand what that means. Now, at this point, we can use the definition of the gamma function in mathematics. So I will not get into the details of the gamma function, but let me tell you that this integral here is just equal to gamma, the gamma function evaluated at n over 2. So it is evaluated at this value. You can see that the integration variable is called r squared. So you can, if you want, you can change the name of this variable to another variable. Anyway, now we have found that this is equal to gamma of n over 2 divided by 2 multiplied by omega sub n. But remember that the same integral is also equal to pi to the power n over 2, right? We have calculated exactly the same integral in here by using a different method. And at this point, we have an equation that we can solve for omega sub n. Omega sub n is equal to 2 pi to the power n over 2 divided by gamma of n over 2. It's as simple as that. So this is the expression for the solid angle. Now, what is the expression for the volume of the sphere? The volume of the sphere can be simply written in the following fashion. So we have to integrate dnx over the sphere, right? And we assume that the radius of the sphere is a capital R. So we know that the variables x1 squared plus x2 squared plus dot 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 plus xn squared, they will have to be equal to capital R squared when we consider the equation for the sphere. But now we go to spherical coordinates, and we know that in spherical coordinates we can write basically this differential, we can write it as r to the power n minus 1 dr d omega. And since omega does not depend on r, you can integrate over r. So when you integrate over r, you integrate from 0 to capital R. So you have integral from 0 to capital R, the radius of the sphere, r to the power n minus 1 dr. And then when you integrate d omega, you just get omega sub n, like this. So this integral will simply give you capital R to the power n divided by n, and then we have to multiply by omega sub n. We have the expression for omega sub n, therefore this is equal to r to the power n over n 2 pi to the power n over 2 n over 2 divided by gamma of n over 2, like this. And then Now you can recast this expression in the following form, so in the following way. If we divide the numerator by 2, we also have to divide the denominator by 2. So we can put 2 here. So you have n over 2 in the denominator, which multiplies gamma of n over 2. There is a simple property of the gamma function, which tells you that basically gamma of z is equal to z minus 1 times gamma of z minus 1. So you can use this property there. This is a simple property to check, but I'm not going to do any derivation here in this video. I have provided other derivations in other videos. I don't remember exactly, maybe in other courses, and in the complex calculus course probably, but never mind. This is quite easy to check also on the internet, and it is not worth expanding on this result. By using that property, we see that this is equal to gamma of n over 2 plus 1. So we can write this in a more compact form like this. If you want, you can write it as the square root of pi times capital R to the power n divided by gamma of n over 2 plus 1. So this is the result for an n-dimensional sphere. In particular, this is the volume of an n-dimensional sphere. If you want, you can also calculate the surface of an n-dimensional sphere. So S sub n. So sometimes, instead of using sub n, it is also possible to use sub n minus 1 for convenience. Why is that? Well, we are in n dimensions, but the surface of the sphere is n minus 1 dimensional. So that's why sometimes you can also see this kind of notation here. But that's not important because that's just notation. So you simply have to take the derivative of the volume with respect to the radius. It's as simple as that. If you think about it, it makes sense that indeed the surface of the sphere should satisfy this simple equation here. Now it is possible to check and expand on the result that we have found here, but I'm not going to expand too much on it. I'm just going to show you that, for example, when n is equal to 2, the surface of this sphere is actually a circumference, so you get a circle. So the volume of the sphere, the quote-unquote volume, will have to give you basically the area of the circle, right? So if we put 2 there, you get square root of pi squared, which gives pi, r squared divided by gamma of 1 plus 1, which is 2. So you have gamma of 2. And by using this property one more time, this property here, so gamma of 2 can be written as 1 times gamma of 1. Therefore, this is equal to gamma of 1. But gamma of 1 is just equal to 1. It is something that it is possible to show. I'm not going to waste any time on that. So this is equal to 1, and therefore the volume of a two-sphere, or a two-dimensional sphere, is equal to pi r squared, which is just the area of the circle. It's quite easy to check. Now if you take the derivative with respect to r, you can see that S2 is equal to 2 pi r, which is just the circumference. It is the quote-unquote surface in 2D of the quote-unquote sphere. So in particular, in this case, instead of using the word surface, I should use the word circumference because we are in 2 dimensions. Therefore, the volume represents the area enclosed by the circumference. And the circumference is just the length. It is just, if you want, the perimeter. It's the length of the curve that defines the circle, right? And you can also check it for different dimensions. So you can set n equal to 3 and try to understand whether you find the expression, the usual expression that you have in 3 dimensions, the 3-dimensional sphere. And it is also interesting to discuss what happens when you increase the number of dimensions, what happens to the volume if you increase the number of dimensions. But I think this is enough for the video. I'm not going to give any more complicated details.